This lesson is going to focus on the acid-base properties of salts and determining the pH of salt solutions. Let's review what a salt actually is in chemistry. Most of us recognize the term salt in terms of table salts that we use at home to flavor our food. But in chemistry, a salt is an ionic substance that is a crystal lattice that contains cations and anions, so positive and negatively charged ions, in a repeating pattern. Salts are electrolytes, so because they're ionic, right, they'll dissociate into ions, they will conduct electricity, they will dissolve in water fairly easily. And the key thing is that salts are derived from neutralization reactions. So you might recall this basic reaction where we take an acid and a base, and it's a double displacement reaction. The products that we form are always water and then a salt. And the salt is derived from an ion of the acid and an ion of the base. Now, you have learned that an acid-base neutralization reaction should be just that, neutral, and give you a pH of 7. And that is true, but we've kind of been lying to you for a couple of years because that is only true if your acid was strong and your base was a strong base. If you have a weak acid or a weak base, the pH of your salt solution will not be 7. So the pH is very dependent on the type of acid or base that you have. And I'm going to stop right here and warn you, don't continue with this lesson unless you have a good handle on how to determine whether an acid and a base are strong or weak. Because if you cannot tell the difference, you're going to find this lesson a little bit challenging. So new this year, we're going to fine-tune our definition of a neutralization reaction. Okay, so when we have a neutralization reaction and we produce a salt as a result, the neutral salt will either produce hydrogen ions or hydroxide ions, and it may not result in a pH of 7. You might have a solution that is actually acidic, even though the solution has been neutralized, or maybe it is basic. And basic salts increase the hydroxide ion concentration. Acidic salts increase the hydrogen ion concentration. And these salts are composed of conjugate acids and conjugate bases. And this is why they may influence the pH of your solution. Not always, but if they're derived from a weak acid or a weak base, you are not going to have a solution with a pH of 7. So there are 4 combinations of salts that we're going to get into. And the first one is the one that you've been most exposed to. So these are salts that truly produce a neutral solution. Okay, and we mean by that a pH of 7. And the only time that this happens is if your acid and the base that you are reacting in your neutralization reaction are both strong. Okay, so in the salt that gets formed, your cation should have been from a strong base. Your anion should have been from a strong acid. And then as a result, your solution will have a pH of 7 because those ions do not interact with the water molecule. And the reason for that is that their K value, so the K value, Ka or Kb of these conjugates is so weak, okay? So small that they don't really react and make any products, okay? They maintain on that, reactant side. They favor the left side. So if we look at any of these salts right here, we recognize that those ions come from strong acids or strong bases. So for sodium chloride, right, sodium hydroxide is the strong base, HCl is the strong acid. And of course, the hydrogen and the OH, right, react to form H2O. So remember that we're only interested in the other ions that are present. KBr would have come from KOH and HBr, and those are both strong substances. And then same thing here, we would have had calcium hydroxide, nitric acid. Those are both strong. So when you have a salt and you recognize that the ions that make up the salt come from a strong acid or a strong base, they completely dissociate in water and you do not set up any kind of equilibrium and it'll be a truly neutral solution. Now, what kind of salts will produce an acidic solution? Well, any salt that came from a weak base and a strong acid will form an acidic solution. And here's an example right here. So here's a weak base. There's ammonia, which is a weak base. There's HCl, so it's one of those binary acids. It's a strong acid. And what that means is any ion that comes from the strong acid, we do not care about it. It does not react with water. It does not dissociate to form any hydrogen ions or hydroxide ions. But this ammonium ion, okay, because it was derived from a weak base, this ammonium ion is what we call a conjugate acid. And because it came from a weak base, this conjugate acid will interact with water and it will form hydronium ion like we see right here. So here it is right there. There's the ammonium ion. This is acting as an acid, a conjugate acid, which is a proton donor. It gives its hydrogen over to water. It forms hydronium, and then it reforms the ammonia or the base molecule. But because we form these hydronium ions right here, this causes the solution to become acidic. And even though you'll have a neutral reaction, meaning that you have no original acid or base molecules, just the salt, that salt actually influences the pH and causes it to be slightly acidic. Now there's the chloride ion from the salt, but again, it came from a strong acid. So it doesn't interact with water. It doesn't have the ability to do so. Its Kb value is so small, you don't make any products. Okay. So here are some other examples of salts that would be acidic. So here's ammonium chloride, which we just saw. There's the ammonium ion again, and then there's that nitrite ion. And you have to recognize that the nitrate ion was derived from nitric acid, and nitric acid is a strong acid. So that ion right there does not influence the pH. So any salt that would make the solution slightly basic is derived from a strong base and a weak acid. Okay, so you have to look for ions that would have been derived from each of these two types of substances. So when we have an example right here of a strong base, there's sodium hydroxide, and there's acetic acid, which we know is weak because it's organic. Then we're going to form water. Okay, so we'll take water out of there. There's the acidic hydrogen. There's the hydroxide to form water. And what's left is the sodium acetate substance. And because the sodium ion came from sodium hydroxide, which is strong, we don't care about it. But because this acetate ion came from a weak acid, this is now a conjugate base that has been produced and will now make my solution basic. So this conjugate base is going to react with water. Remember that bases are proton acceptors. He's going to take a hydrogen off of water. He's going to reform the acetic acid molecule. And then what's left is the hydroxide ion, which causes the solution to be basic. There's that sodium ion of the salt. It is from a strong base, so it has no reaction. And so only salts that were derived from weak acids will make the solution basic because of the conjugate base that gets produced. So there's my sodium acetate molecule. Here's potassium fluoride. Potassium would be derived from KOH. This is a group 1 hydroxide. That's a strong base. Fluoride would have come from HF. That is the one binary halogen that is weak. And so as a result, this fluoride ion is the conjugate base that would make the solution basic. Now, what happens when you have a salt that is derived from both a weak base and a weak acid? Well, now it's not so easy to determine whether you are going to have a solution that will favor an acidic or a basic side. Because both of these acids and bases are weak, then that means both of their conjugates that get formed can influence the pH. And so what we have to do is a little calculation, and we have to use this formula right here. Kw equals the Ka times the Kb. Now, Kw is a value for the dissociation of water. And this value is 1.0 times 10 to the negative 14. So this is a number you need to know. And then we say that that value equals the Ka times the Kb of whatever acid or base you're dealing with. So we have to do a little bit of a calculation. And if the Ka is greater than the Kb, our solution is going to be acidic. If the Ka is less than the Kb, or that the Kb is going to be greater, then the solution will be basic. So let's use this formula right here, this ammonium cyanide salt, and let's calculate the Kas and the Kbs of that and determine what pH we should be getting. So what we need to do is we have to calculate the Ka and the Kb of these two different ions. And in order to do that, we have to understand what acid or base these conjugates were derived from. So the ammonium ion would have come from the ammonia molecule. The cyanide ion would have come from the HCN molecule. And we have to recognize that this is a conjugate base and that ammonium is a conjugate acid. And so what we'll do is we will calculate the Ka of the ammonium ion, and we're going to use this formula that we have learned already, Kw equals, Ka times the Kb. So we are still solving for the Ka, so what we're going to do is we're going to take the Kw and we're going to divide it by the Kb of the base that ion was derived from. So the Kw value is 1.0 times 10 to the negative 14 that we use. And the Kb for ammonia, you go off to your data booklet and you will find the Kb for ammonia being 1.8 times 10 to the negative 5. Negative 5. So when we do the math and we rearrange that, we're going to get a Ka value of 5.6 times 10 to the negative 10. Now we have to do the same thing. So we sort of split it in half. We have to do the same thing now for the cyanide ion. So the cyanide ion is the conjugate base. So we have to calculate the Kb for the cyanide ion. And we're going to take Kw and we're going to divide it by the Ka of its acid, which is HCN. And we set it up, 1.0 times 10 to the negative 14. We divide by the Ka of HCN. And again, if we go into the data booklet, you'll find it there, 6.2 times 10 to the negative 10. And we'll calculate the Kb. And we get a Kb value of 1.6 times 10 to the negative 5. So what we want to do is recognize which one of these ions is going to dissociate more in water. And we know that the magnitude of K, right, the larger the K value, it implies that we're going to make more products. Well, if you have a larger Kb, then you're going to make more hydroxide ions. If you have a larger Ka, then you're going to make more hydronium ions. And right now we can tell, based on these values, this is our winner. Okay, this is the larger K value. Therefore, my solution will be basic. So just to wrap up, so since the Kb of the cyanide ion is larger, we're going to have more hydroxide ions produced in that particular salt solution. So when you get those salts from weak acids and weak bases, there's a little extra work because you got to do some calculations. But for all of these scenarios, the reaction of an ion with water to produce acidic or basic solutions is termed hydrolysis. Okay, so that is what we're looking at here in this particular lesson. Take a second and try to determine the pH of these salts. So look at the formula identify, which ion would have come from an acid, which one would have come from a base, would they have been strong or weak, and try to determine what the pH of these solutions would be. Call me over and I'll be happy to check your answers. So let's take this knowledge of salt solutions and let's dissolve some of these salts in water and determine the pH of the solution. So what would the pH of a 0.2 molar solution of ammonium chloride be? So very first thing that you have to do is this internal dialogue in your head, and you say, okay, ammonium chloride, which of these ions came from a weak acid or a weak base? Well, the ammonium ion would have come from ammonia, which is a weak base. The chloride ion would have come from HCl, which is a strong acid. So we do not care about the chloride ion. We are interested in the ammonium ion. And that ammonium ion will be dissolved in water, and it's going to react with water a little bit. And you have to recognize, what is the ammonium ion behaving as? And it is behaving as a conjugate acid. Okay, so it's a conjugate acid, which means it's a proton donor. It's going to give one of his hydrogens away. We're going to form the hydronium ion. So we know our solution is going to be acidic, and we're going to reform the ammonia molecule. We want to know the pH of the solution. So the initial concentration of my ion is 0.20 molar, okay, because it's a 1-to-1 ratio of ions right here. We still don't care about water. Initially, we would have no products formed. Over time, the ammonium ion will decrease by X. My products will increase by X, and we'll have 0.20 minus X as the equilibrium concentration for the ammonium ion. Hydronium will be X and ammonia will be X. So this is step one right here. We are setting up a Ka expression, right? This is a conjugate acid and we're forming hydronium ions. So we need to set up a Ka expression. And so we're going to put our products over our reactants. And the only little wrinkle is that oftentimes you are not going to find a Ka value for these conjugates. So you have to calculate it yourself, okay? But you know here, this is the base that it was derived from. So you're going to calculate right here the Ka of the ammonium ion by taking Kw over the Kb of ammonia. And when you do that, so when you take 1.0 times 10 to the negative 14, and divide by 1.8 times 10 to the negative 5, you get a value of 5.6 times 10 to the negative 10. So we're going to insert that over here. So 5.6 times 10 to the negative 10 is equal to x squared divided by 0.20 minus x, okay? And still, something in your mind should go off and say, okay, that K value is pretty small, 10 to the negative 10, that's crazy small. You can check off to the side, do you need to neglect x? And trust me, you'll be able to neglect x. So we're gonna cross multiply our K value by 0.2, take the square root, and get an x value. So when we rearrange and we solve for x, we get an x value of 1.06 times 10 to the negative 5. So the good news is this x value is for hydronium, and they ask us to solve for the pH. So we're going to quickly calculate the pH of my salt solution by taking the negative log of the concentration of hydronium, subbing in that 1.06 value, and we get a pH of 4.98. Remember, with pH values, we'll always go to 2 decimal places. So there you go, taking these applications of equilibrium, acid-base equilibrium, and applying them to salt solutions.